breaks are a bit short, but we had so many companies that wanted to join this journey. So that's why the breaks should be a bit longer, but this is the best that we could get. So for the next break, we are now 5 minutes over time. We need to be back on time, okay? Great. So now we're going to watch demos from Plants&bytes and DNV. And these two contendants will show a more fundamental solution to interoperability. They might not answer directly to the use case. However, this fundament is crucial. So we are very glad that they want to be a part of this journey. So first of all, welcome to Manfred Theisen from Plants&bytes. The DXP Association has developed the de facto standard for exchange of PNIDs and data graphics between different tools. In the interest of wide applicability, DXP provides features to include information that is not covered by its information model. And it does not prescribe details such as the appearance of PNID symbols. However, seamless PNID exchange in a given context, such as disk, requires a common understanding of details beyond the DXP and PNID specification. What is the exact geometry of the symbol for a ball valve? Which information about the pump is mandatory at a certain project stage? Current practice is the costly and error-prone manual configuration of all involved tools. And they will demonstrate how the PNID profile editor simplifies the captures and management of such details in a vendor-neutral format based on the DXP specification. Welcome, Manfred.
Okay, thanks a lot for the... Yeah, thanks a lot, Tanja, for the introduction, and good morning to everyone. So, I'm going to talk about profiles, and probably it's a hard question, what is a profile? In this context, you may hear it for the first time. And it's also probably the first time you hear about PNB, so just a few words about our company, PNB Plants&bytes. We are quite a small company, founded 5 years ago by Markus Sömers, my colleague, and myself. And what we have done in the past years are several tasks in the domain of supporting digital plants. This includes services. For example, we have created a verification tool for the DXP Association. More about DXP later. And services also include that we have supported Equinor in the past 2 years in the disk DXP project. So within the entire disk frame, there is one, let's call it, sub-project about DXP. And DXP here means data exchange in the process industries, and DXP has developed in the past a standard for the exchange of information about piping and instrumentation diagrams. When I say exchange, this includes both the conceptual information independent from any graphics, such as what equipment is there, what kind of piping is there, how is the topology, how are the things connected, and so on. And on the other side, DXP includes graphics. So the task that we had to solve, or we had to contribute at the DXP project, was that the goal was to enable the seamless exchange of PNIDs between quite different tools. So several software vendors are involved in this disk DXP project. Now, the answer in principle is simple. Let's use DXP and let's exchange the information. This works from one point of view because DXP defines how to transport the information. But there is still something different, something in addition that has to be clarified. When we talk about PNIDs, people may have different opinions about how they should look like. They may use different symbols for the same thing. They may have a different understanding of what kind of equipment classes or piping component classes are required. Others may say, okay, I need this attribute, where other people say, oh no, that's not important, I need some other attribute. And that's what we call profile. So profiling the general DXP information model in a way such that it meets the requirement in the specific context. In this case, the context is disk, which is such a general agreement made by Equino and AKBP and others, how PNDs should look like. So in practice, what has been done, not by us, but by Braga, which was also involved in this DEXP, is that they have, in quite a lot of work, collected the information underlying this disk profile. For example, they have created a very huge Excel table with all the different equipment classes that are required. DEXP itself defines a few classes, pump, centrifugal pump, and so on. But for disk, we need more equipment classes and piping component classes and much more. And they also collected the attributes. And in addition, they have drawn the symbols. How should this look like in the graphics? And an exact definition with predefined geometry, with predefined positions where, for example, for piping components, the pipes should attach. And all these are conventions that are really important if you try to exchange PNDs between different tools, because just assume the pump is a bit larger in the target tool, it has to rearrange the graphics. So DEXP allows it how to transport the information, and the profile gives additional requirements on how this should exactly look like. Now, as I said, we, Plants and Bytes, did not specify the profile, but our task in this disk project was to create first example files, and second, we should have to extend an existing verification tool we had already created before for disk, such that we will be able to check disk DEXP profiles, whether they are compliant with the overall specification, DEXP specification plus the disk requirements. So in order to do this, we somehow had to gather all the information from the Excel sheet, from the different SVG graphics, put everything together into one, let's call it database. It's just some internal data structure in order to create the example file and the blueprint. So and the verification tool. So I just show you this very quickly because this is definitely not the focus of the presentation today. This is the standard DEXP verificator extended with functionality for disk. You see this is one of the disk compliant example files that we had created. On the left hand side, and that's why I show you this, you see the basic structure of a DEXP model, so the conception model. We have actuating systems, and we have, of course, different detect plant items or equipment types, what people normally call them. This is a conceptual model, and this is a graphics model. And in disk, we have extensions on both sides. On the conceptual side, we have additional classes, and the graphics side, we have predefined symbols. So that's sufficient for the old verification tool. In total, this has worked, but it was quite a lot of work. First for Braga, because they had to use existing tools such as Excel and Visio for creating the input. And for PNB, for us, it was also quite a lot of work to access the information, because these two formats are not really pleasant to read. Then our idea was, okay, for future profile extensions, or for completely different contexts, when other industries, medical, pharmaceutical, chemical, whoever, wants to define their own profiles, or want to extend an existing profile because some new equipment is on the market or whatever. So this will always be an ongoing task, and that's why we thought it would be very good if there would be some profile editor, and that's now the focus of the presentation. Took a long intro in order to explain why we think such a profile editor is quite useful. So in this profile editor, you see currently I've imported 3 profiles. One is the DEXP profile. In other terms, that's the DEXP information model, because that's the base for everything. We'll see how later. The second profile is the actual disk profile. That's where we have defined the model extensions and the symbols, and more about the last layer, if I have enough time at the end. So in the DEXP information, DEXP profile is just essentially just a copy of the DXB information model, what classes are in DXB, what attributes are defined. I'll skip this. It's just a reproduction of the DXB information model, the publicly available specification. So again, DXB is the base. And then, based on DXB, the DXB profile, we have created the disk profile. And there are two things. One of them is that we have extended disk. And those of you who will know perhaps UML may see some terminology that they know. For example, we have added additional classes, just some acoustic noise reducer, which is just a new disk-specific supertype of the existing DXB piping component. And here, one general remark about the user interface. So we are in late alpha. The user interface is still a bit clumsy when it comes to these things. When I switch to the graphical parts, the user interface will look much nicer. Okay, so one point of disk is extending the information model. We have also cases where we take an existing class from the DXB information model. In this case, it's the equipment class. And there we add an additional attribute called typecode, specific for disk, not available in DXB here in addition to the DXB information model. So the other point where we have to capture profile information, and this looks much more interesting, is when it comes to the symbols. And I just take the very first one. This circle is a graphical representation of a process instrumentation function, so the typical instrumentation bubbles that we often see in a P&ID. So this is a very simple one. Let's take this one, that's a bit more interesting. So in the editor, you have the option to change these things to standard graphical operations. Here you can also change things like colors, line widths, all these typical drawing things. We have lines. Most of them are just lines. This one's a bit more interesting. We have text. We could, for example, change the text if I want to, or change the fill style of the symbols and all those things. So this is already workable and also usable. But symbols is not just about the graphics. I already took these piping symbols because they have to be connected via piping. No, I mean piping connections. Piping components are normally connected via piping. And here we have to capture information where these piping connections should be done. And these are, of course, not part of the symbol itself, but let's say additional information. What we have set here is, okay, I'll just move it here, and you can better see it. This is where some piping connection point for this symbol. So the connection should be located here. And this little dot just indicates what is the direction of the pipe that starts here. In disk, it's quite simple because normally lines are vertical or horizontal. So normally we just have these in 90-degree steps, but you can change them and set them wherever you want. Second instrumentation point here. And other things have piping connection points, and other things have instrumentation connection points. So back to the first one, just a simple circle. These are the 4 connection points for instrumentation lines. Second, detailed information that we need for the graphics is which information is represented in the diagram. And these A, B, C are just placeholders for labels. And such a placeholder first contains the information about the graphical appearance, so which font, which color, which position, which text alignment, all those details. But the more interesting part is, so this is label C, what's the information that is represented here. Okay, I could show you this if I go through the data structures, but this is really not very well readable, so we have this short button to just give it in a quite short form. So what is here? Just show this label one here. This is a process implementation function, and then the text that should actually be represented here is composed in the following way. We start at the process implementation function, follow one association called parent structure, Then we arrive at some process plant object, which has this attribute, some plant identification code, and this is what should be represented there. Normally, this example, it's normally just a single letter, simply the letter that identifies the process plant in which the PIF appears. Then we have some literal minus or separator minus sign, and then we have a second attribute, again, not of the object itself, but we have to follow a reference. So go to the plant system to which the PIF belongs and use this attribute. So and these are, of course, not just names, but these are really predefined or profile-defined attribute names that are available in our information model. Just this one, at this place, the label is a bit simpler. It's simply the tag type attribute of the PIF itself. So altogether, we can collect information of the graphics here. Now, the profile is also more, there are also constraints. So far we had extensions. We have extended the profile to get the required expressiveness, but there are also some restrictions. And to give you some examples, in the disk profile itself, there are very few restrictions. Things like if something is a piping component, then it should be one of the predefined piping components, and so on. And given that not too much time is left, I will go to the next profile. So this profile is just a basic disk profile with the general disk requirements. But there is something more. If we have a look at some development project, there are different stages. And at different stages in a project, normally the requirements with respect to data become more and more strict. And as an example, we have considered one stage called FL0 for whatever reason. And at this stage, we have additional requirements. So this profile is a further extension of disk itself. No model extensions, but just additional constraints. Quite a lot of them, and let's just go to the text representation. So in simple terms, this example means if something is a process plant, then the value for the identification mode must be given. In general disk, at the early stages, it may be missing, but at this defined FL0 stage, it must be defined. So I hope to get some basic idea of how we have created some information model that allows us to define such a profile, and that we've created a tool, and it's also web-based because we think it will make usage much simpler because these things are normally used by different people, edited by different people. That's why we have decided to make this as some web tool. Now, as we are already doing this web development, we also decided to re-implement our existing verificator for DXP, simply because this was a desktop tool. Okay, web tool is much nicer. So this is admittedly in early alpha stage, looks a bit like the old desktop-based DXP viewer, but now this one is also web-based. And because we have created a general framework for data that can be modified, we also decided, okay, let's not just make it a verificator, but let's make it some DXP editor, again alpha. It's not much more I can do at the moment, but what we have here is some web-based PID editor whose internal data model is completely DXP. So there are never any issues for DXP export or import, simply because the tool itself uses the DXP information model internally. Our main, of course, we are not planning to make this some competition product for the big engineering suites here, but we developed this tool because we very often had requests by small companies, small EPCs, and so we just wanted to create DXP PIDs in a very simple way. They don't need some suite, they just need some drawing tool, but with a good DXP export format. That's why we have created this tool. What I would have liked to show you is also how I can import the profile, but this was probably not enough time to finish this for today. So in case there will be some further event in the future, we will also hopefully be able to show you how we can import the profile into the P&ID editor such that, yeah, you get a profiled P&ID editor which with those shapes are refined and those requirements that have to be met in a certain context. One final remark, DXP itself is planning to develop some exchange format for profiles, and we, of course, are happy to bring our ideas and our experiences into something which will hopefully be the official DXP exchange format for profiles in the future. Yeah, that's it from my side. Thanks a lot.
Thank you so much, Manfred. We have a technical committee with us, and now Jan will give you some feedback on your demonstrations.
Thank you very much. This was very much appreciated. Now, folks, we are down into the details. Now we are picking on the tiny bits and pieces that needs to fall in place to make things interoperable. And getting a profiler, I think that is a very good option for the Norwegian continental shelf, the Nordsjok, to agree on the profile they would like to see in the DXP exchange. And of course, having a tool for small, medium-sized companies, I think it's great. Thank you.
Amazing. So Jan is a part of our technical committee. Can the technical committee just rise and wave to the audience? So the technical committee, at the end of today, they will give out some prizes because they are the ones looking into the demos, and if they have actually answered our questions and kind of have a rating. So we have a competition here. Good. Okay, next up is DNV. DNV is driving digital transformation by providing comprehensive solutions for managing and securing data across its lifecycle. In this session, they will demonstrate two innovative tools. The I/O tool, which facilitates collaboration in developing ontologies and knowledge graphs, and the EQM, which ensures data quality at critical points in the data value chain. While these tools focus on enhancing data management and integrity, DNV also offers robust cybersecurity solutions that protect the entire data chain. Together, these offerings provide a complete solution for organizations looking to strengthen data governance, quality, and security. Please welcome Dirk Walter, Pål Rylandsholm, and Carl Jon Pedersen.
Thank you very much, Tanja, for the introduction. So we are here to demonstrate the two tools we have in place, and we are developing these tools because we believe they will help industries actually achieve trust and efficiency for both their physical and digital assets. And in our presentation, if it's coming up, how do we do that?
It's not showing.
Well, anyway, I'm going to give a short introduction for why DNV is doing this and why we are on stage here today. And then I'll try to be short, and then these two guys are going to demonstrate the actual tool we have in place. It's a PC thing. Problem between chair and computer, I guess.
Duplicate?
Oh, here it
Way
is.
to duplicate? I just duplicated the screen?
Yeah.
Okay. It worked before? No.
Okay, there we are.
Go back.
I think so.
I'm going back. Okay, so let's start. So the goal, I think, for DISC and for industries as such is not to develop ontologies or models or anything like that. It's about getting efficiency, robustness, and value out of the assets that you have in operation and which you are developing. And DNV, we have for 160 years been doing assurance of these physical assets as such. Mainly in the maritime industry from the start, but also in the energy industry and later on other industries as well. DNV is a well-known company for this around the world. What might not be that known, DNV, we also have over the years gained similar experiences in the digital area of industries. We are a software house. We have been providing industry software since 1969 when we published our first commercial software. We are experts on data quality, information modeling, and ontologies. We have our own platform we provide to enhance collaboration through data sharing in industry. That's Veracity. And we have also 10,000 digital twins operating in our production system for commercial ships worldwide, actually for our customers. So we can truly say that we have the expertise sort of both on the digital side of the business and on the physical side of the business. And we are able, I think, to assess digital solutions that are in place, and we're able to guide our customers through the digital transformations that's actually taking place now these days. And to help industries, we have issued a series of recommended practices. We're doing this together with the key players in the industries. I'm not going into the details of all of this, but these are used for framework around with our customers, framework for successful digital transformation and to gain value from digital investments that are being done by our customers and by industries. It should be mentioned that the one called the Asset Information Framework, which DISC has a very high stake in and ownership to, that's going to be issued now by the end of September this year. Then it's finally coming out. And we are constantly updating this framework, and we are trying and striving to that these standards are going to be in compliance with other regulations, EU regulations, and other industrial standards out there. And from this framework and from our experiences, sort of this illustration or conceptual architecture has emerged from our side. And I think this is illustrating, I'm not going into the details of this either, but it's illustrating the interplay between the digital part of the business and the physical part. So data is generated from the physical asset. It's transferred and it's taken into the digital side of the industry, where the ultimate goal is to have a data-driven operation. But for this whole thing to actually take place in a good manner, you need to trust that the representation of your physical asset is of high quality. And for this to happen, we think that the continuously assessment of the quality and the trustworthiness of the data and the models and the representation of your physical asset in the digital world needs to be in place, and that's an enabler for this kind of business. And we will demonstrate now 2 tools we have in development, actually trying to assure the trustworthiness of the representation and the quality of the data you have in your businesses. And that's the IO tool, which is going to be demonstrated by Dirk. It's the industrial ontology tool. It's, like Jan said, we're now way down into the details of stuff, but it's about bringing other people to the table, the engineers and those who need to have the saying when you're digitizing requirements and digitizing actually your asset as you go and you're having data for this. And then you have the IQM, which is it's a digital quality inspector, we can say, which can be deployed all around here, and you would get quality indicators from the inspector stating that these things are in compliance with the requirements you have actually told the inspector to check for. Before I give the word to those guys, I must say we are using the demonstrator on data we have in-house already. We're going to show you that. We're not using the data that has been provided by DISC, but we truly believe that what we are demonstrating will actually map nicely into the use cases for the digital commissioning, digital sort of brownfield, and for the greenfield case that is coming from DISC. So I really hope that the technical committee will give us some credit for that. And by that, I'm giving the word to Dirk, who will show you the I/O tool.
Yeah. Thank you, Paul. So now I'm going to talk about the I/O tool. So DNV has a lot of experience in building semantic-based solutions. And a guiding principle has always been to separate data from the application in order to allow liberating the data, to avoid vendor lock-in, and to promote interoperability. And for that, it is important to represent information in a standardized and semantically precise way. We are developing a tool for creating large-scale information models in form of ontologies. And we call it the Industrial Ontology Tool, or short I/O tool. And we aim at making it strong for industry, enterprise level. Okay, so creating large-scale ontologies cannot be done by one person only. So it requires the collaboration between domain experts and experts in ontology engineering. And this is what the tool supports by allowing to onboard different people in projects, giving them a role with certain capabilities and access rights. It also allows to reuse existing content. Information models are developed by different people. They are maintained and governed by other organizations. And this tool allows to reuse that information. It also makes it possible to publish new content in an API, for example, for consumption by applications or to simply send queries against to inspect the content. But it also allows to export the resulting ontologies so that they can be used totally independently of this tool. So no data is being trapped. I would like to talk about one use case, a project that we are participating in together with ABLE and other participants, such as the University of Western Australia. And together with them, we work on a valve ontology. The idea is to describe valves as they are being specified in industry standards. And this forms then the knowledge base for a valve selector tool, and that tool helps experts in narrowing down the choice of suitable valves, for example, in various phases in engineering and design, such as procurement in a project. So to this end, I will change, hopefully this works, to my web browser, yes. And I will browse to the address of the I/O tool. And I'm being welcomed. This is the I/O tool. I sign in, so the tool knows me already. The identity provider is DNV's Veracity data platform. Should only take a moment, and then I'm in. And I'm being greeted by my name. So the tool knows me, and I can inspect and make changes to the user settings here on the top right. In the middle, we see the different projects I'm involved in. We also call them workspaces. I can toggle between a list view and a tile view. I can create new workspaces, and I can, of course, search, for example, for my valve workspace, which is this one. Then I can change my role. Now I'm a super user. I can just choose my role. If you are assigned a certain role, this may not be possible. So now take the role of a subject matter expert, and I enter my workspace. Then it looks like this. The title of the workspace is here on the top left, together with the versioning number, which should appear, yes, and when it was created. On the left, we have some basic information, some metadata about the project. And here on the right, you see what has happened in the project. This is all the history. And when we scroll down, you see a lot has happened here already. So this has been a quite active project. And this project is synchronized and versioned using a Git repository. And the provider of that repository is GitLab. It's a little small, but it's written here. And I can follow a link to the repository here on the top right by just clicking on it. And it should just be a moment, and then I see this project in GitLab. This could be GitHub, Azure DevOps. This can be is very flexible. Okay, so now as an SME, my task is to describe valves as they occur or are specified in specifications in standards. For that, I go to the tab data files and I search for example for Equinor's TR2000 standard. And I see there are a couple of data files here. For the sake of time, I will skip that part and go to the next. And this TR2000 standard references other standards such as API standards, ASME standards. And let me just open an ASME file. So this is a data file. And here it opens. It is shown in form of a table. The I/O tool features all the sorting and editing facilities that you would hope for when working with a table. So we can adjust the layout, we can hide and show certain columns, we can of course create new columns, delete them, and the same for the rows. We can filter per column for rows that we are looking for, we can edit rows, we can delete them, and we can copy them. So let's have a look at the first row, which specifies a class in the ASME standard, namely the ASME B1610 ring type joint end valve. And this one has a particular property, namely it has exactly 2 flanged ends of a particular type, which is this one, ring type joint gasket contact face. The SME would know what that means. And if that's not correct, or if this class was being edited here, the subject matter expert could open this drop-down list and choose the correct class. And you see there are classes here referring to other standards. Probably they have been made by other SMEs, for example, when we import information into the project. What is being shown in these drop-down lists can, of course, be configured in the tool. One more feature I would like to show here is this lookup functionality. The raw view of the data is really just identifiers, which is not very helpful. As an SME, I would have to look up what these identifiers mean. And therefore, we have a feature to look up this information for us and then show what is relevant to know what we're talking about when looking at a particular identifier. Now I can make my changes. I can edit this table and other tables. And then we follow the Git operations to persist these changes. So I can look at what has changed in my tables, in the entire workspace. I can commit and push the changes. I can pull from the repository. And I can request approval of my changes to make them visible to other users as well. Okay, so now I would like to change my role. We are kind of short in time.
1 minute.
Okay, I changed my role quickly to the ontology engineer. I enter the workspace, so the ontology engineer is now responsible for making sure that the data entered by the SME ends up in the right ontology, in the right format, following modeling patterns. Let's have a look at how this is done. The ontology engineer is also responsible for configuring the entire architecture. And this is how it would look like in this project. There are lots of ontologies. This graph shows ontologies. Each node is an ontology. The arrows between the nodes represent the import relationship between ontologies. The green nodes are the imported ontologies, the so-called library ontologies, and the blue ones are the ones that we are working on in this project. Let's go all the way to the left. We find the upper level ontology IDO, the industrial data ontology. We have some metadata shown here, and we can inspect the ontology in detail. This is the RDF graph shown in turtle format. We can toggle the view between the graph view and the table view, and we see these are all the ontologies listed here. The files that contain these ontologies, if there's an identifier given, I can click on the identifier and I come to the home page, for example, of the industrial data ontology as hosted by PCA. I can go to the content ontologies that we are working on. I can click on them, and for example, I go to my ASME ontology, and I see that this one consists of various parts. These parts need to be generated. One part is one data file together with a template. These templates are given in Otto syntax, but other syntaxes can be understood by the tool as well. I can generate the part to create out of the table an RDF graph. We skip that here. I can show you at the stand later. And one more thing I would like to tell you is by changing the role to the super user, I can set up new projects, I can onboard new users, give them certain access rights. I can also define schemas for identifiers that are being generated in a project. The I/O tool understands as well UUIDs and GUIDs as is common. Now, one last thing before I finish and hand over to Carl-Jon is something I would like to just tease. The I/O tool has now a better feature as well, namely talking about requirements. The idea is we want to digitize requirements in DNV and make it possible to automatically verify requirements against asset models. This is something I have no time to talk about here, but I would like to talk to you about at the stand. So please come and visit. This information, to build ontologies, we need high-quality data, and this is a job for IQM. And with that, I hand over to Carl-Jon.
Okay, thank you very much, Dirk. It's always... We started late. It's always good to come last, but I'll go really fast. I've got 2 minutes. As mentioned in the introduction, the industry is moving from docking-based to model-based work processes. And we have to have good quality data throughout. At the end of the day, we want trusted decisions. That involves ensuring we have good data quality. We have to have management and governance. We're not going to look at the organizational part of that today. We're going to show a technical solution, which we've been developing, called the IQM. This is, if we look at a typical project, if we look at a typical project, it's a very complicated landscape. You've got data coming from everywhere, from different partners, subcontractors, and so on. The I/O tool is within the data processing and holograph, but what the IQM we're going to talk about covers all of these areas to ensure that we have good quality data throughout this data flow. And what we're developing is something called the Data Quality Inspector, or IQM. It's a standalone containerized microservices which customers install in their own infrastructure. There's no vendor lock-in. Interoperability is in focus, and applications talk to one another. And the only part that DNV is involved in is writing the data quality rules, which are then implemented in IQM. And then IQM runs a process, checks the data according to data qualities, and creates an output on that. So what we're going to show very briefly here is we have some data going on the bottom. This is data from engine exhaust temperature data. It's obviously not real time, but we have a file running that. And IQM is set up on the left-hand side with 3 rules in this example. It's looking for outliers, noise, and drift. So this is sensors data. It checks the data in real time. And we see number 1, 2, and 3. That's where it's picked out the outliers and noise and the drift. And the users, when they use this, they can then see where they're having problems with their data, and then they have to come up with mitigating actions. Typical general actions are that you will improve sensors, increase maintenance, and so on. In terms of the IQM example, the I/O tool example we showed earlier on, we may be importing 1,000 or so data lines. We want to make sure that that data is of good quality. There's no missing chunks of data. Did I import everything? Are there any duplicates? Do all have data names? And are there any data quality checks? This is a small example, but fits into the bigger picture of how we need tools to create business value in greenfield, brownfield, and in operation. We would like to show you this in more detail if you want to come and talk to us on the stand. These are our contact details, and we can talk a bit about general trust and recommended practice. Thank you.
Excellent, DNV. I ticked off some boxes, so you can relax. You will get some points. And we saw now the I/O tool, which is an enabler for managing the ontologies and handling the data that we need. And quality, yes, it's so important. Thank you.
Thank you.
So yes, the next break will be a bit shorter. So, okay, last slide was Albert Einstein, and now we also have Newton here. Because Newton, in the 17th century, he formulated the laws of motion and gravity. And these laws, they were considered absolute truths. However, in the 20th century, Einstein introduced his theory of relativity that challenged Newton's law, because they saw that these laws that were considered absolute truths, they did not apply under complex conditions. So under extreme and complex conditions, these laws didn't apply. So the foundation of physics turned out to be a part of a larger and more complex picture. And I think the same goes for us. We need to look at, as the times are changing faster and faster, the bigger picture is more and more important. Okay, have a nice break. Be back here at 11:15 promptly.